Welcome and thank you for attending today's webinar, Importance of Fluidic Control and Precision in Serial Activation of Ionic Channels. My name is John Batista and I will be the moderator for today's presentation. The Smart eFIS division of Harvard Bioscience is an authorized distributor of ion flux technology. As you will see, ion flux is a benchtop instrument that permits the elaboration of both ligand and voltage-gated ion channels in a high-throughput manner in both single-cell and ensemble measurements. Today's presentation will be delivered by Dr. Ali Yahia, who is joining us from Fluxion Biosciences, the manufacturer of the ion flux platform. Before we begin, I'd like to address a couple of items concerning the webinar. First, this webinar is being recorded, and after the event, everyone will receive a link via email to that recording. Second, if you'd like to ask a question during the event, feel free to type your question into the Q&A module at the bottom of the presentation window. Please note this menu auto-hides and may require you to mouse over to see it. At the end of the presentation, we will have a question and answer period where we will try to answer as many questions as time allows. If we do miss any questions, they will be answered directly via email. With that, please allow me to introduce today's speaker, Dr. Ali Yahia. Ali is an experienced electrophysiologist with an extensive background in automated patch clamp. He has been working in the industry for more than 13 years. He received his PhD in cardiac electrophysiology from McGill University in Montreal, Canada, and is now the VP for Ion Flux at Fluxion Biosciences. I will now turn the floor over to Dr. Yahia.
Thank you, John, for this nice intro. Today, I would like to talk about the importance of fluidic control and precision in serial activation of ion channel, which actually represents a nice introduction to the flux mercury system. So just a little bit of a background about Fluxion Biosciences. The company was founded in 2005, and our headquarters are now in Alameda, California, in the Bay Area. We have three main product lines, all based on microfluidics technology, hence our logo, and catering to different disciplines. First one is liquid biopsy with Isoflux Systems Citation Manager, Spotlight 59. Sorry, I'm having issues. Second one is cellular analysis, Bioflux 200 and Bioflux 1000 systems. These systems are used for live cell imaging under flow, and they cater to microbiology, immunology, oncology, and hematology. And of course, Ion Flux and Ion Flux Mercury. These are the two new updated systems for the Ion Flux technology. Now, Ion Flux evolved quite a lot from the initial prototype. Gen 2 showed the first commercial introduction of Ion Flux in a 16-channel format. The introduction was done actually in a bar where everybody kind of drank beer while the machine did some experiments. It was pretty nice. The Gen 3 showed an upgrade of the system internal, allowing for Ion Flux HD to be introduced. Ion Flux HD is a 64-channel system, and Ion Flux Mercury, or Gen 4, is the latest iteration. So Ion Flux Mercury is now a fully integrated automated patch clamp system with amplifiers and operating computer inside of a benchtop box. As before, it comes in two flavors, Mercury 16 with 16 amplifiers and Mercury HD with 64 amplifiers. These are the specs of the new system. So as you can see here, the size is 50 centimeter by 50 centimeter by 25. So they are quite compact, and the system can fit on a benchtop. In fact, you can fit it on a trolley and move it around as long as you provide pressure, vacuum, and power. It has integrated temperature control with a heat source right on the plate. A cooling system can be purchased separately in case you needed to do these experiments. You can use ensemble 20 cells or one single cell for gigaseal recordings. And current clamp is also optional. Now, the main thing about it is that you can also do maximal sweep lengths of 300 seconds. So the machine can actually record without any interruption for 300 seconds if you set the frequency to 0.5 kilohertz. That actually, I will show you a little bit of experiments about that later on. Now a bit about the principles of operation. So the system uses SPS plate format, 96 well for 16 and 384 well for HD. The bottom of the plate is replaced by a laminar flow system, allowing for in-plate compound delivery and continuous flow, as is shown here. So each plate is divided into zones. So you can see here, you can see 4 zones for HD and 2 zones for 16. Within each zone, we have experimental patterns. We have 8 experimental patterns for HD and 4 for 16. Now, if we take one of those experimental patterns and we look at it closely, we have 2 traps, which are denominated by T1 and T2 here. And this is where we have intracellular solutions and where the cells are trapped. Each trap has its own independent amplifier channel. And so in each experiment, we have 2 independent recordings for the same experiment, for the same conditions, in fact. So we have an independent source for the cells termed in. I know it's confusing. Most of the time people think it's intracellular. It's not. It's actually in for the cells going in extracellular solution, and an independent out for waste, which is this guy. In each experimental pattern, we have 8 compound wells. That can contain whatever you like, different compounds, agonist, antagonist, whatever is needed for the experiment. Each of those compound wells has its own microfluidic conduit, so there's no interaction between them until they actually get to that point. So this means that there's no crosstalk between them, there's no contamination. Everybody is living in its own well. Just to look at how it works. So this cartoon shows you how the system actually works in brief. So once the wells are filled and the plate is inserted, all solutions are primed. And then the cells come in from the in well, and with suction, they get trapped at the trapping well, as you can see here. So each one of them will actually also perform extra suction on the cells, and then whole cell patch clamp is formed. Here we go. Okay, this video shows the process of trapping the cells. The plates are actually transparent and access to them is very feasible. So in effect, you can shine light or record the cells while they are trapped. Here you can see the cells are flying by, then the flow is interrupted, they are trapped, then the flow starts again, and then new cells, and then they get interrupted again. So the flow gets interrupted again, and then basically this keeps on going until all of the holes are covered. And you can see afterwards how the flow just continuously go after. Here we go, flow is moving. Okay, so once the cells are trapped, the compounds are released and recording is done. In its simplest form, watch steps are simply adding gaps between the compound releases. As you can see here, as soon as we turn off the compound, this is basically a watch step. So compounds flow at the same speed towards the cell and are washed at the same, basically at the same speed. So with mercury, the speed can also be controlled. Okay, so to summarize, we have 32 experimental patterns. Each pattern can have same or different cell types if you choose so. So we can actually have 32 different cell types on the same plate. Now this is extreme, but you can do it. We have 2 different intracellular solutions per pattern, which also gives us 64 recordings. However, you can also have 64 different intracellular solutions per plate. Again, this is extreme, but you can do it. So in fact, one single plate can have 32 different cell types and 64 different intracellular solutions at the same time. Now, if we count a little bit the data points, if we have 256 compounds per plate, and each compound is added twice, with the extracellular solution, we get about 576 data points per plate, measuring 32 different extracellular solution data point. Which means that we get 576 data points per plate, and therefore, if each plate takes 20 minutes to finish, and sometimes they can actually be faster, and you do 3 plates per hour, so you can effectively get 1,728 data points in 3 hours. In 6 hours, you have 10,368 data points per day. Yeah, this looks like it's a bit of a bit of an extreme. However, it is not, because you can see from the slide actually, which was done from Pfizer, what they did is that they were able to achieve 1,408 data points per plate, as you can see from their calculation, and they were doing 4 plates per day, and then the current throughput became 8 plates per day, and then they were projecting 20 plates per day, which is much more than 10,000 data points. Now, of course, if you want to do this, this might be a bit difficult to fill up these plates by hand. So you can definitely attach it to a liquid handler. Since the plates are SPS standards, any plate handler can fill them up, but you can also attach them to a T-can like this, which actually will perform complete automation, including plate filling and plate feeding. This T-can can control up to 4 iFlux systems stacked. And you can see here how it's actually feeding the plate into the system. So it can actually treat it like a plate reader, which it actually looks like. Okay. Now for this talk, I'm going to look at 4 case studies. The first case study is going to concentrate on how the fluidic control will actually give better responses for nicotinic receptors. The second case study will look at the continuous flow and sodium modulation studies. And the last one will look at GABA receptors assay flexibility. All of these studies will actually show some of the features of the system. And these case studies actually came from different customers, and they actually represent, some of them represent data which is just like, which is basically initial data, so it's not completely published yet. Okay. Now this cartoon explains a bit about the mercury fluidic control system. So because everything is actually happening in the inside of the plate, the flow and everything, the compounds actually reach all the way to the main channel. When the main channel is actually flowing, the pressure is exerted on the compound. And as the pressure is exerted on the compound will go backwards, and the diffusion layer will appear between the main channel and the compound. Now, in order to fix this, all iFlux systems deploy what we call a backflow pressure. What the backflow pressure does is that it will attempt to minimize this problem. However, if that backflow pressure is actually set to a very high level, it might actually push the compound out, and therefore will have some problems. So what do? Is that we actually, in all systems, in all historical iFlux systems, this is actually set to 80% of the main channel. And therefore, you basically don't have the compound going all the way backwards, but at the same time, you still have a tiny bit of a diffusion happening between the main channel and between the compound itself. Now, what happens is that as time goes by, as this diffusion will start to increase bit by bit, and therefore you'll start to get variability in the addition of ligands, and hence the reason why you see compounds, hence the reason why you see currents not really superimposable because of this variability. Now, with the iFlux mercury, what we did is that we enhanced the system in such a way that we allowed this backflow pressure to be 98% of the main channel. Now, by having it 98% of the main channel, the additions of the compounds are much more precise. And that's exactly what I would like to show you now. I would like to show you how this became very precise. Now, in order to test this, the best way to test it is with acetylcholine receptors. And here, what we tried it with first is with Te671 acetylcholine receptors. Now, the Te671 are actually rhabdomyosarcoma cells with a native acetylcholine receptor. And the currents are actually initiated by adding ACH. However, if ACH stays around, or if it is added in a very small amount, or streaked into the main channel, for example, then the cells will desensitize and will need some time to recover. So basically, what we did is that, as you can see here from this experiment, this experiment was actually published. It's not from us, but basically, what will happen is that as you actually get further and further away from the first desensitizing step of acetylcholine, as the current will start to recover. And we did something similar to this in our lab, and what we So first, we tried it with the original ion flux, which is Gen 3 here. And you can see here that the first one, which is the pink one, was after an addition of 30 seconds, and the second one, which is the purple one, was after an addition of 100 second delays between the desensitizing step and the second addition. Now here we're adding 1 millimolar ACH, which is a saturating amount. However, you can see basically that it did recover very nicely, actually after 30 seconds. However, you can see that there's a bit of a delay between one and the other. Now we repeated this with the mercury system. You can see that that delay disappeared. In fact, they're nearly superimposable. We also noticed a variability from well to well. A decrease in variability from well to well. So here, this is actually we did the same experiment here, but with 27 wells or 27 cells, if you want to, and we normalized the currents to the last current in the experiment. So what happens is that you can see that basically there's a bit of a run up and a bit of run down, which is normal, what you see there. But at the same time, when we standardize this, you can see that the first additions were very variable. Some of them were actually much less, and some of them were much higher. So the variability was very high, and as you got further and further away, as the variability became less and less. And you can see that the variability with mercury became much, much less, and also the run up and run down became much less also, where the currents were much flatter. So much more precise in the way that they're responding. With the help of urethane, we also did some data on alpha 7, and the same way we looked at the same steps, a desensitizing step first, and then afterwards following steps with a prolongation, and we noticed that actually the first one here, the first step here, which is very small and actually superimposed, is after 6 seconds. And the second one is after 510 seconds. And you can see here which is expected recovery of the current. However, what we saw and we did not expect is that when we tried it on the mercury system, the 6 seconds and 510 seconds were basically superimposable. So it means that the current actually recovers much faster than what we anticipated. And you can see that it does actually goes up and it goes down, but they're basically superimposable, the first and the last. And when we looked at multiple cells to see that if this is happening, we noticed that this is in Gen 3. You can see that that there is mostly a recovery, and in the mercury, it's mostly flat. So even though we don't completely understand exactly why it's recovering so fast, much faster than what we anticipated, it's still very good. It's still very precise and very superimposable. Now for the second case study, I would like to show some of the data from a poster presented by Dr. Mike Arpad this year in biophysics. So he was looking at the gating effect of riluzole on NaV 1.4. So a bit of background about it. Sodium channel inhibitors act in two major ways. Channel block, which is the physical occlusion of the pore, or a pore blocker, and modulation, which produces inhibition by stabilizing one of the channel's native non-conducting conformations. So riluzole is a good example for a drug that acts mostly by modulation of the channel and has a strong state dependence with a minimal inhibition at hyperpolarized potentials. You can see from the shifts here how it works. So what they did is that using mercury, they did these experiments, which are pretty neat, and that's why I would like to show them here. You see, they did several voltage steps to measure state-dependent onset, which is termed SDO, recovery from inactivation, RFI, and steady-state inactivation, SSI. So all of this was done in one single 1-second sweep. Currents from these sweeps are plotted below. So you can see for each of those steps, they plotted the currents. You can see them here. Then they added 30 micromolar riluzole, and as the effect from the drug started to appear, they plotted it as 20 consecutive currents from light to dark. You can see it here. It's actually being plotted like this. So the black ones here are before, and as riluzole came in, as it started to actually decrease here. Now, the sweeps with all of the steps were repeated for 1,684 seconds, while 30 micromolar riluzole was added and washed, followed by 10 and 30 micromolar imipramine, then 30 and 100 micromolar trazodone, and 10 and 30 micromolar chlorpromidine, tongue twisters. For each condition, SDO, RFI, and SSI, they plotted the peak for all of the steps and superimposed the IT plots, as you can see here, showing the effect of the drugs at the different conditions, with black being the control. Each drug application was repeated twice. This is the first time, and this is the second time. This experiment clearly demonstrates the ability of the system to wash away compounds. So it's really neat in a sense that you can actually see the effect of the drug and then actually being washed, and then you see the effect of the drug again and being washed. And you can also see the gradient of the effect of the drug based on the different steps that you're seeing here. So the black one is the first step, and the light green one is the last one. And these are the gradients for these steps here. And as they're being plotted on top of each other, you can see the drugs going in and out. Now, for our last case study, we did an experiment to study GABA current reversals. This was done actually at University of Florida, and it was during the initial setup of the instrument. So just a brief intro here. So GABA receptors regulate most of the fast inhibition of the mammalian brain. They are target for multiple drug types like sleeping aids, anti-anxiety medication, and neurosteroids. Now, in most general form, they are made of 2 alpha, 2 beta, and 2 gamma subunits. In this case, or basically in this case study, we looked at GABA A alpha 1, beta 1, gamma 2L, and GABA A alpha 1, beta 1, gamma 2S, which actually differ by only 8 amino acids. So we're going to term them here S and L. And basically S and L, they show different distribution in the brain. However, when you record from them, they kind of look very similar to each other. Now, part of that case study, what we did here is that the customer was saying that most of the automated patch clamp recordings that we see were actually done with a chloride reversal of 0. So he was saying that isn't chloride reversal in the brain at around -60? So he was saying, why don't we just actually try 2 intracellular solutions, one of them with a reversal of 0 and one of them with a reversal at around -60 millivolts. But they also had two cell types that they want to try, and they also had 2 extracellular solutions that they want to try. So we said, why don't we try all of them on the same plate? And this is exactly what we did. So, so we used zone 1 and zone 2, zone 1 for the long form and zone 3 for the short form. So basically we divided the zones here. So this is zone 1, zone 2, zone 3, and zone 4. And we divided the plate into 2. And we used these 2 zones for the long form and these 2 zones for the short form. Then what we did is that we added ICS1, which is, I believe, the one which actually reverses at around -60 in here. And then ICS2 we added in here, which means that each experimental pattern will get to see ICS1 and ICS2 with the same cells at the same time. And then, of course, we added the 2 different extracellular solutions, one here and one here. And then each of those had GABA concentrations, GABA dose response concentrations, which were added with their own extracellular solutions. So in effect, if all of the experimental patterns will record and everything goes great, then we should have 32 different recordings with GABA with the L type and 32 different recordings with the S type. And we should have 16 recordings with ECS1, 16 with ECS2, and of course here also 16 with ECS1 with the S type and 16 with ECS2 with the S type here. And of course, each one of them will have 8 with ICS1, 8 with the ICS2, and as we go on. Now, for the experiment, we did a dose response. So these are the IT plots, actually. You can see that there's a dose response here, and then we followed directly by an IV curve. And the IV curve, so the cells were held at -80 millivolts. The calculated reversal for ICS1, as I said, is -60, and for ICS2 is 0. And the displayed IT plots for the experiments showing the dose response followed by the current responses elicited by 100 micromolar of GABA under changing voltage steps. So basically we achieved 90% success rate. There were a couple of wells, as you can see here. This is n equals 7, I think. There were a couple of wells which did not respond, and that was not actually a problem with the cells. It was a problem that we did not insert proper compounds into the plate. So the wells were actually killed from before the experiment started. So if we did not do these mistakes, it would have been even higher than 90% success rate. Still, that's pretty high. And you can see here that the dose response for the reversals, which are at -60, are showing smaller currents at the same scale around as these guys. And if we look at, these are the L, and these are the short, and you can see all of these lines are actually data which is coming from different wells, all at the same time, all from the same plate. Then, of course, we plotted a few of the dose responses here. They're superimposed. There were a few concentrations which were decent, and then afterwards it was a bit saturating. However, we were able to calculate EC50 to be between 3 and 5 micromolar. And then afterwards we calculated the IV curve with the standard deviation between the cells, and you can see how it is reversing at different levels. At first sight, we noticed that there wasn't that much of a difference between the IV curves between the L and the S. However, when we looked closely, and I don't know if you can see those lines, they're very thin. What happens is that with ICS1, we noticed with the L type, it actually flipped at around -54.5 millivolts, and this is n equals 7. And with ICS2 at 14.5 millivolts. And then the S-type flipped at -49.5 millivolts and 24 millivolts for the upper level. So it showed us that a little bit that the S-type is a bit shifted in its IV towards the positive side. And that was something which we did not see before. So again, all of the experiments which I'm showing here were all done on one single plate. It kind of shows you basically how flexible the system is with regard to the fluidic control that you can do. So in summary, the mercury system enhances the capabilities of the ion flux in precise fluidic control, providing great capabilities for studying complicated assays, and the open plate design combined with continuous flow allows for ease of use and speed in heterogeneous assays. And I would like to thank David Haiyang Wei from Eurofins, Mike Arpad from I can't really pronounce it, from Otvis Lorand University, and Eric Wang and Belinda Pinto from University of Florida. Thank you very much, and now I'm ready for questions.
Thank you, Ali, for a great presentation. We'll now open the floor for questions, and I've already received some here. Let me just navigate to the, okay. So the first question is, can you use the same plates in both the 16 and the HT system?
Well, so basically they both use SBS standard plates. However, the ion 16 has a different layout with regard to the way that the electrodes are set up, and therefore it uses 96 well SBS plates. The HT uses the 384 well plates because of the way that the layout of the electrodes. You cannot take the plates from one and put it in the other. However, you can use on one system, you can use single cell plates or ensemble plates. These are interchangeable, but it has to be the same style of plates.
Okay. Do you provide an upgrade path between the two systems from the 16 to the HT?
Yes, there is actually an upgrade path. So the mercury systems, you can upgrade from the 16 to the HT. Basically, within the first year, if you upgrade within the first year, it is a cheaper upgrade than if you upgrade later on, because the machine will, as long as the machine is within its warranty, then it's an easier upgrade path. If the upgrade path happens later on, then it might incur extra costs. But yes, there is an upgrade path.
Okay. And regarding software, is the software included with the system, and how many licenses are provided?
Yeah, so the software, actually, we have a unique way of providing the software. So the software itself is divided into two different divisions. First of all, the software is included with the system, and you can install it on as many computers as you like. And the way that the license works is that the license is actually attached to the system itself, meaning that the software which is installed on the system will have its own license, while you can take the software for analysis and assay development and install it on as many computers as you like, but that software will not operate a machine. So that way, basically, it makes it much easier, much more flexible for people to build assays, whatever they like, and then send it to the machine to operate.
Okay. Can primary cells or stem cells be used with the system?
Yes, they can. So you can use primary cells as long as the cells are in large quantities and they are more homogeneous in a way, so that you can have the best success rate possible. But you can use any type of cells as long as they are spherical, they are suspended, and they are in large quantities enough that you can actually get meaningful experiments out of them. So yeah, I mean, primary cells which are very rare might be difficult, or weirdly shaped cells like cardiac myocytes, for example, are going to be nearly impossible. But T lymphocytes, like all sorts of cells which are in large quantities will actually work. The same thing with stem cells too. Stem cells will do exactly the same way too. You just actually there are a couple of papers in our library which talk about primary cells and also stem cells.
Okay. Thank you. So that's all the questions I have, or that people have submitted. I wanted to thank you again for this very informative presentation. And let me put up our contact slide here so that people have the ability to get in touch with us. So thanks everyone for joining us today in this introduction to IonFlux. We enjoyed engaging with you on the subject and appreciated the excellent questions that you submitted. If we missed answering any of your questions, we'll get back to you via email, and you should be able to see a slide that contains our contact email address, which is us-sales@smart-ephys.com. So thanks again for attending, and we hope you have a wonderful day.
Thank you.